Hello again. Thanks for tuning in. I have a few more things to say about probability and some of the vocab and terminology we're going to be using quite a bit. So we'll just get right to it. Classical probability, or that phrase, is basically when we're talking about what should happen. You know, when you talk about a particular event, you know, whether you're flipping a coin, drawing a card. And this is the kind that you're used to. You know, you can think of it as a ratio of the number of outcomes in a particular event divided by the total number of outcomes. Versus empirical probability, which just means what did happen. So you actually conduct an experiment. You know, you create that frequency histogram that we did already. And, you know, you have the frequency of an event over the total frequency. So you've actually found these when you found those percentages on your frequency diagram, where you tallied stuff up and put it over a ratio. Those were examples of empirical probabilities. And so you kind of have this idea of comparing, you know, what should happen statistically versus what did happen. You know, statistically, you should lose the lottery every time. But empirically, you know, at least one person wins every time. And so there's chances that you can compare. So this kind of leads into the next kind of idea, which is called the law of large numbers. And basically what it says, it's not that crazy of a thing, but it says, you know, as you increase the number of examples or experiments. Maybe example's not the best word, but what it says is that, you know, empirical probability, you know, should get closer to classical probability. And let me just explain this with an example. You should never, statistically, you should never win at a casino game, a game in Vegas. You know, whether you like blackjack or roulette or, you know, any of the games out there. But people do win. That's maybe what brings them back to the casino. But the idea is, if you win the first time and then play 10 more times, you're not going to win all 10 times. And as you increase the number of times you play, the percentage of you winning is going to approach what should have happened. You might win once, you might win twice, but you play 100 times, and it's going to balance out to the empirical probability, and, you know, where the odds are on the house. If you didn't like that example, you know, think about flipping a coin, you know, a bunch of times. You might flip the coin the first time and you get a heads. Maybe you flip it again and you get a heads. Maybe you flip it a third time and even get a heads. This is not what should have happened, because you should get half heads and half tails. So maybe you flip it, you know, 3 more times and you get this. Still, not what should have happened. You should have half heads and half tails. But I'm saying if you flip that coin a bunch more times, you know, maybe 20 times, 100 times, 1,000 times, the more you do that, the more tails are going to get inserted in there. And eventually, the higher you get, the closer you're going to get to what should have happened, which is half heads and half tails. That's what the law of large numbers says. All right. So, some more facts about probability. The range of probabilities. So anytime, many times you'll be asked to find a specific probability. And the range goes from this. The probability of an event could go from 0, and that means that it's impossible to happen. You get a probability of 0. What's the probability that you roll a single die and you get a 7? There's no 7 on the die. That probability would be 0. It's impossible. Versus if you get a probability of a 1, that an event is certain to happen. You can also think of 1 as 100% if you're a percentage type person. And so all other probabilities kind of fall between this. And the closer it is to 0, the less likely it is to happen. And the closer it is to 1, the more certain it is to happen. Again, you can tile these to decimals and percentages also. Another thing I want to talk about is something called the complement. Complement of an event. And I did spell it correctly. It's not a compliment like, oh, she complimented me on my eyes or something like that. Complement of an event. Let me kind of demonstrate this with a picture, and then we'll explain it. So if we have a sample space that we'll represent with this rectangle. And we talk about the event, we'll call the event E. That's part of the sample space. Maybe your event is flipping a heads on a coin. Then anything that's not part of that outcome, we represent with this little apostrophe, and that stands for the complement of an event. And the idea here is that, let's get used to the notation. It looks scarier than it is. The probability of an event happening plus the probability of the complement of the event. You could think of the complement as the not the event happening. Has to be equal to everything. The event and the complement of it, so the event and the complement of it have to make up the entire sample space. So if you think about the probability of getting a heads, on a fair coin it should be 1/2. Well, you can think of the complement as the probability of not getting a heads. This is the complement of heads. Now, it sounds funny. I'm trying to make a point by saying not heads, but in this case, the complement is just the other piece of it, which would be tails. And we know that that should also be 1. And so if you're thinking about this formula, that makes up the entire sample space. Let me do one that's got a little bit more depth. Let's say that you flip a coin. I just did that one. Let's say you roll a dice. And let's say the event is the probability that you roll a 1. Well, if you roll a dice, the whole sample space is, you get one of these numbers. There's 6 possible outcomes, and the probability that you roll a 1 is just a 1 out of 6. But if I'm using the diagram that's up here, the event that I'm referring to is here. And so the probability of the complement of rolling a 1, so, not rolling a 1, sorry for my grammar, is essentially the same as the probability of rolling a 2, a 3, a 4, a 5, or a 6, which would be 5/6. And so again, notice that if you think about the event plus the complement of the event, you get the whole thing. So just kind of a few more verbal examples. You know, if you're talking about a deck of cards and the probability of a king. We'll get into this in my next video, but probability of a king is there's 4 kings out of 52 cards. The complement you could think of as not a king. And the idea is the complement would be every other card that's not included in that. And so sometimes when you think about this formula, and this is worthy of your notes, when you have an event and you have the complement of event, whether it's cards, dice, or some other example, sometimes you can be slightly clever and, you know, you could use a little algebra here and say, well, the complement is 1 minus the probability of the event. All I did was, you know, subtract a probability from both sides. You could also say that this is equal to 1 minus the probability of the complement. Again, I'm just adding and subtracting things from both sides of this equation. And so all of these are equivalent expressions, but we'll see sometimes that you can use these, and we'll do a bunch of examples in class too, not just on the videos, where you can kind of be clever about this and manipulate things to get answers quicker. There's also some good examples in the slides that are available online if you haven't checked those out. Okay, I'm going to stop there and do an additional video just so I don't run short on time and get cut short. So thanks for watching, and I'll see you soon.